All right, folks, we're going to take a look at an overview of the Ellis Model 1800 bandsaw that we have here in the shop. The basic operation is pretty straightforward. Essentially, we're going to make sure that the machine is plugged in. We'll give it a general overall safety check, make sure that things are in good working order. Come around to the back side of the machine, and we will take whatever it is that we want to cut. In this case, I'll just grab a piece of pipe from the rack. I'm going to raise the head, lock the head in the upright position, secure the material in the vise. Then I will lower the head down and get it within about 1/4 of an inch or so of the top of the cut. I don't want to let the blade actually touch. If I were cutting a specific length, then I would want to loosen the vise at this stage of the game, measure that, and then go ahead and retighten. But for purposes of demonstration, we're just going to make a cut. So I would, at that point, put on my safety glasses, release the emergency stops on the back side here, press the power button, and then I would set the down feed speed. Once the cut is complete, carefully remove the part that we cut. It is sharp on the edges. It could also be hot. And then put that part into service. In this case, it's a piece of scrap. I'll put it in the attachment bin. At that stage of the game, we would remove the stock from the part. And if we had to make additional cuts, we would go ahead and reset and we would do that. So the overall operation of the machine is relatively simple. What we're going to do now is we're going to take a look at the details of those steps one at a time. All right, the first thing we're going to talk about is an overall safety check of the equipment. We'll cover specific areas of this in other videos, but for right now, what we want to do is get into the habit of, open the doors, just give this a quick look. You can take the blade and give it a general inspection. It's difficult to see lots of the blade. For example, the area up here without a flashlight, again, it's hard to see. You can't manually turn this, but you do want to give the blade a general inspection and make sure that it's working correctly. Once that's done, we'll check for the alignment. The blade should extend out past the guide roll here by, 1/8 of an inch to the bottom of the gullet, to the teeth approximately. It should absolutely not be rubbing on the back side. Right here you can see where it was at one point rubbing against the paint, probably during an adjustment process, but there should be room behind there between the back of the blade and your fingers. Additionally, we should have the same condition on the other end. So this end here where the motor is attached is the drive end, and this is the idler end. This end also allows us to make adjustments to the blade when we get into the maintenance portion. We want to give the guide rolls a good general inspection. Make sure that they're in serviceable condition. We have a shiny spot down the center of this roll, but if you feel with your finger in here, we do not have a deep groove worn in. Okay, that would be a possible reason why the machine isn't cutting straight. We want to check the opposite end for the same thing. The rolls here should be, again, in good condition. They shouldn't be worn on the top or the bottom. They may appear to be worn, but again, that could just be a light coating of oil. And by simply rubbing that with my finger, I can see that that line that's there is just on the surface. It's not actual wear. In order to close the door here, I have to push this release in. This will swing shut. It locks in a Velcro enclosure. Same thing on the other end. I have to push this in, and then this door will close. We want to make sure that this wheel is in fact in place and that it's loose. This rides along the bottom of the blade to help knock the chips off. In terms of the back end, there's really nothing here except for this adjustment, which should be tight. Up towards me is tight. If I push this away, it's loose. We'll go over that when we talk about making beveled or angled cuts. The springs here are adjustable, but again, they're not really designed to be user adjustable. I check those a couple of times a year, and again, I'll talk more about that in the maintenance portion of the video. But suffice it to say that this knob back here should not be touched by the students, okay? If I come around to the back side of the machine, I want to make sure that when I lift the machine up, I'm grabbing from this handle right here. This is an adjustment for the tension on the blade. These screws here adjust the tracking of the blade back and forth. And again, we'll talk about that when we get into changing blades, but we want to lift the handle only from here. If I continue along, I have an emergency stop button. If I push that in, it should pop. And when I turn it in the direction the arrows indicate, it should pop back out. The power button is here, okay? It should operate freely without damage. It's not going to come on now because the saw is all the way down. And additionally, there's an auto shut-off feature right here, okay? I have an adjustment knob here that adjusts the how much of the blade sticks out, this extension. This arm comes back. This is kind of a weird setup, folks, as it should be tight when it's turned in the clockwise direction, but if we loosen it, it will also retighten in the counterclockwise direction. But again, this is intended to be tight clockwise, normal lefty-loosey, righty-tighty configuration. In order to adjust this, we only need to loosen it just barely. Then this will slide to expose more blade or less blade, depending on how big of a part we're going to cut. Then we need to make sure this is, again, tight before we actually make a cut. The back side is adjustable, but it really never gets moved because even though it looks like there's a lot of clearance here, if we angle the saw, that clearance will quickly disappear and this guide will bump into the back of the backstop. The adjustment piston, there shouldn't be oil leaking or dripping all over the place. This is a knob that adjusts the down speed, okay? When this is all the way in the closed position, where essentially it's turned, clockwise until it's tight, the ram will not allow oil to leak through and the head will stay up. So I'm going to lift the head up right now. I'm going to grab here and I'm going to lift the head up. With the head up, we can see the auto stop. Again, this screw, when it comes all the way down, needs to hit this radius curve. That's why it's there. That pushes this up and it flips this switch. So right now we're just going to do a quick check of the electrical system while we're right here. Again, auto stop is on. Nothing happens. I'm going to release the auto stop. The machine is started. The blade is moving, okay, at high speed. And then when the blade comes all the way down, as long as this hits on this curve, this should flip this switch and it should stop the blade, okay? Again, it should restart and then I should be able to press the auto stop and shut it off. It should not restart with the auto stop depressed. So again, that is a check that you would want to make before you use the saw. Back down to the adjustment valve. Again, this is either working or it's not working, I guess, and that maybe that goes without saying. But when this is in the closed position, the head should stay up like it is now. That allows you to put parts under the saw. If I open this, this will allow the head to come down, and I will make adjustments as necessary. So right now the head is dropping very slowly, and again, if I open this up more, the head will drop more and more and more rapidly. If I open it all the way, the head would basically come slamming down to the ground. Around the back side, if we take a look at the motor, this electrical outlet is not really intended to be used for operating power tools or drills or anything like that. There are other features that this saw doesn't have. There's an air system that allows to cool the blade. That would be plugged into there, and it would come on automatically when the blade starts turning. So that outlet is dead until the power is turned on. So that's not going to do you a whole lot of good. Don't plug your grinder or your shop vac into that, okay? If we open this lid up, we have a pulley system. This is not intended to be adjusted by the students, but again, if you had problems with the saw, you may find that the belt is worn and this may need to be replaced. Ultimately, this sets the blade speed, and that speed has been preset for the material that we weld here in the shop, which is mild steel. Essentially, when we turn the saw on, the blade is moving. Of course, it's going around in a loop like this, but an individual portion on the blade is moving at 200 feet per minute, okay? And that is the linear travel speed of the blade. The vise itself, I'll lift this up and take a look at this. The vise itself is movable. Underneath, I'll bring the camera down and point this up. There is an adjustment nut right here. You can reach underneath with your hand. So from the top view, again, I would reach below. This does not need to be taken off. It just needs to be loosened a little. The vise can move back and forth to grab material, and it may be necessary to move the vise if we're cutting at an angle. For the most part, this is relatively stationary. You want to check that nut. That does occasionally come off. And if it does come off, there is a nut and a washer that both need to be in place. Without the washer in place, it will not stay tight and it will damage the plastic nut. Additionally, the vise has a quick release feature. So I can move this over. This is called a half nut, and you'll see why when I bring this around. There are threads in half of this. It's only half engaging. So by removing that, it allows me to make rapid adjustments to get a hold of the part, okay, to get it in the ballpark, and then I can of course close this, secure it, and then I can tighten the vise down. Additionally, this pin right here can be removed, and the entire vise assembly can be moved backwards in roughly 3-inch increments, and then the pin has to go back in, and it needs to go back into the hole underneath. When the pin is in the locked position, it will be all the way down to this shoulder. So right now the pin is not in the down position, and I'm going to slide this forward, and there it is in the down position now, okay? So that pin should go all the way in. So you first want to make a coarse adjustment. I would generally move this back. I would pull the pin, and again, for 9 cuts out of 10 folks, this will be in the forwardmost position. And I'm going to drop this in place. I know I'm moving around a little bit, and I got lucky and it went all the way down in. So as long as my part will fit in there, I would leave this in the forward position. There's an adjustment here on the front for mechanical stop. This part will move out, allows us to swing this up to have a mechanical stop for the part. So if we're cutting parts repeatedly, we can use this instead of having to measure every time. The screw is upside down, so make sure you're turning it in the correct direction. Finally, there is a chip tray underneath, which is now full of chips and small parts. But again, this needs to be cleared out periodically. All right, for basic cutting operations, right now the saw is set at 0 degrees, and we're going to go ahead, back this thing up, and we're going to make a cut. What I have now on the saw is a piece of flat bar. It's 1 inch thick, 5 inches wide. I've got the flat bar standing up on its edge, and the blade that I have is a Starrett Versatix blade, outstanding saw blade, by the way, if you're looking for a better saw blade than what you've been using for cutting structural steel, interrupted cuts, the Starrett Versatix is awesome. I wish they were paying me to say that, but it really is. In this shop, we went from going through maybe 8 to 10 blades a year to 1 to 2 when we switched over to the Starrett Versatix. And this is a high school shop, so stuff gets just abused, okay? It's being used by trainees that oftentimes, well, they do stuff wrong. So, at any rate, it's a great blade, but it's a variable pitch blade. That means that the number of teeth on the blade in a given inch changes. And that changes anywhere on this particular blade from 4 teeth per inch to as many as 6 teeth per inch, okay? Other blades that we use in the shop, I have a blade that's just out of reach here. I'll grab it. Other blades that we use in the shop are 2-3. So this is a Starrett Versatix blade as well. And the pitch on this blade varies anywhere from 2 teeth per inch to 3 teeth per inch, and we also have 3-4. So the reason that we have different blades is because we have different thicknesses of materials that have to be cut. Essentially, there's a consideration that has to be made as soon as we decide that we're going to cut a piece of material, and that is, in the case of this flat bar, do I cut this standing up or do I cut it lying down? Okay. In order to make that consideration, we have to look at how many teeth are going to be in the cut. So if I stand this bar up on its edge, I'm going to bring the saw in. I'm going to reach over and lower this blade down. What I will discover is that at 90 degrees, and I'm not making a 90-degree cut right now. I am cutting at a, well, the actual cut is at 90 degrees, but when the blade is at 90 degrees, which it's not until essentially the cut's over with, but at 90 degrees, this blade, when it's at a 4 pitch, 4 teeth per inch, because this is 1 inch thick, there would be 4 teeth in the cut at any one time. When the blade is at a point where there is an average of 6 teeth per inch, there would be 6 teeth in the cut at any one time. At an absolute minimum, we want 3 teeth in the cut, and that's ideal. Essentially what would happen is if we only had 1 tooth passing through the material at a time, if we had a really thin piece of material and we were cutting maybe sheet metal, then as the saw is progressing down and 1 tooth comes along and rips out a piece of that steel, the saw could progress down considerably before the next tooth behind caught that piece of steel. So the feed rate would have to be very low to prevent an individual tooth from taking out a huge piece and breaking the tooth off. Additionally, that will cause chatter. The teeth will go through in a thump, 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 thump manner, cutting through maybe 1 at a time. So by having a minimum of 3 teeth in the cut, that ensures that the blade travels down through smoothly. Okay? On the other end of that spectrum, we could have as many as, say, 20 teeth in the cut, which would be the extreme upper end. If I took this same piece of material and I laid it down on its side, which I'll do now, and I lower the blade down, we can see quite clearly that at some point in time, just before the blade passes through, we would have a tremendous amount of teeth in the cut. Now, this is a variable pitch blade, so there isn't really a portion that has 4 and a portion that has 6. It just varies between those two, and that's for to prevent harmonic issues and vibration and things like that. But essentially, for simple math, if this is 5 inches wide and has 4 teeth per inch, we would have 5 times 4, 20 teeth in the cut. At 6 teeth per inch, 5 times 6 is 30. So at a minimum, we're going to have approximately 20 teeth in the cut at a fixed pitch blade. Now this varies, so it's going to be a little bit different, but the idea being that we're pushing the upper limits of how many teeth should be in the cut simultaneously when we lay this part down. The reason for limiting that is fairly simple. When the tooth comes down, and like my finger, if it hits the top of the piece of steel, if this saw frame represents, you know, the corner of this angle bar kind of blown up, and an individual tooth comes down, that tooth hits and it scrapes, and as it scrapes, it rolls up a chip. It curls up a chip inside the gullet of that tooth, okay? The tooth behind it is also going to take a cut, because remember, the blade is dropping the entire time. So as this tooth comes in and begins to scrape, if it's 4/1000ths of an inch deep that it takes off at this end, by the time it gets across to the other end of that piece of flat bar, it is more than 4/1000ths of an inch deep, because the blade is dropping, okay? So that initial cut, because of the angle of the blade, is getting deeper and deeper. The tooth behind it, as it travels through, will hit slightly lower. And it's relying on the fact that the previous tooth took some material out, so it's taking, again, maybe a 4/1000ths of an inch depth of cut. That continues tooth to tooth to tooth to tooth. Well, when a single tooth, for example, goes down through, it doesn't take a lot of downward weight or downward pressure on the saw to keep that tooth in the cut. When we add 2 teeth, it takes more pressure. 3 teeth, more pressure. And eventually we get to the point where there are so many teeth in the cut that the saw will not actually be pushed into the part and make a cut. An example of this would be the old, laying on a bed of nails, okay? And it's about pounds per square inch. If someone were to sit on a single nail, they would have a nail shoved into their flesh. But if they lie down on a large number of nails, their weight is distributed over such a large area that while I'm sure it's still painful, it doesn't puncture them, okay? The same thing happens here. With only 3 or 4 teeth in the cut, the weight of the saw is enough to keep the saw cutting. With 20, 30, 40 teeth in the cut, the weight of the saw is not enough weight to keep it cutting. So you might think, well, I'll just push down on the head to help it cut. Again, now we're risking bending the blade and damaging the blade. So we never, ever, ever push down on this saw. This is preset, given the springs on the back side that I said earlier we don't touch, so that the weight at the head here, when the saw blade is just barely off the deck, about 1 inch, is approximately 8 pounds, okay? So that's not an option. The option would be, if I wanted to cut this lying down, is put a blade on that has more, a coarser pitch, fewer teeth. So if I went to a 2-3 pitch, and there were 2 teeth in the cut per inch, upwards of 3 teeth in the cut per inch, and this is 5 inches wide, there may be between 10 to 15 teeth cutting simultaneously, okay? So that's what we do. The other issue is if that individual tooth has to travel a long distance, and as it's cutting, it's curling a chip up in front of it. Think about a butter knife going across the top of a soft pad of butter, rolling that curl up, okay? That chip is inside the gullet of 2 teeth. And eventually that gullet will be full. And when it's full, you can't push the blade down anymore. But yet, we're trying to, because there's weight on the head, and the end result is that it breaks the tooth off. And when it breaks one tooth, the tooth behind it, because it's falling at the same rate it was before, is now taking out the amount of material that 2 teeth were taking out previously. That tooth will quickly become overloaded and break. Then the tooth behind it is now taking out the amount of material that 3 teeth were taking out previously. And you get the point. Essentially, when we lose one tooth, we usually lose about 6 or 7 inches worth. And it's just a instantaneous machine gun fashion, the teeth are gone. So we've got to keep an eye out on the loading and the way that we're going to make these cuts. So we're not going to cut this in the downhand position. I'm going to lift this up. I'm going to lock the blade in the upright position with the knob on the back side. I'm going to stand this material up very carefully. I am not cutting a prescribed amount of material. I'm just making a cut. So again, I'm going to move the drawing, the vise in. I'm going to drop this half nut, make sure that this is engaged by turning it, and then I'm going to put the locking lever down. I'm going to tighten it. The question that a lot of people ask is, How tight? You shouldn't need a pry bar to get it loose, folks, okay? It does not need to be excessively tight, but it needs to be tight enough to keep the part from moving. The reality is that as the blade comes down and pushes on this part, it is forcing the part into this backstop and into this corner. And for all practical intents and purposes, I could almost cut the flat bar without the vise holding it at all. It doesn't need to be that tight. A piece of pipe, something that can spin, a piece of part that's shaped awkwardly that may flip or roll, you have to tighten it more. So you need to use your judgment, and again, that's only going to come with experience. But for right now, make this good and snug. If you find that you're having a great deal of difficulty getting it loose, you probably over-tightened it, okay, and you'll learn over time. So I'm going to bring the blade down. If I had a cut line, I would align that with it. If I were making a cut of a specific length, my preferred method is to take my rule. In this case, I have a combination square tape measure. I like to measure directly off the blade to the end of the part and then move the part back and forth. That way I know I'm going to get a good accurate cut. A soapstone line is marked off of this, and then you're lining that up to something else. So my preference is always to, again, put the tape measure directly on the blade and then measure it to the end, and you should get a very accurate cut. So that having been said, I'm going to fire this thing up. Again, I'm going to check the emergency stop. It is already in the out position. I'm going to press the power button, and I forgot something. We'll stop. This adjustment right here, this is excessive. So I want to make sure that I have enough blade to clear the part, but I don't want to have so much blade out there that the blade can wander. So I'm going to loosen this adjustment screw. Again, it only turns about half a turn at max. I'm going to bring this in. I want to have clearance. I usually think about 2 fingers worth. Essentially, I want to have a minimum of clearance and a maximum of, say, for example, 2 inches. Okay? So we're going to tighten this down. We'll go ahead and we'll start a cut. Loosen the E-stop again. Press the button. I'm going to set the down feed. So right now, I'm just simply going to set the down feed so that the small ball that's on this knob lines up with the black line. Essentially, we want to set the down feed while we're cutting so that the saw engages the part slowly, and then we increase the pressure until the saw is cutting under a fair amount of weight. We're looking really at the chips coming off the back side, and we'll have to talk about that in another clip or close-up. But you don't want the blade going through so lightly that it's rubbing the material off, and we don't want it going through so heavily that it is shattering or vibrating or bouncing or making bizarre noises. So it takes a little bit of experience. For most material in the shop, there is a small silver ball on that screw. You line it up with the black line, and you're in the ballpark. Okay? Cutting feeds and speeds could be an entire 40-hour course for a machinist. So we're not going to try to get into that in detail in this video. But again, you can see that on a thick piece of material like this, with this particular blade, which is good and sharp, it takes some time to cut down through. When it gets all the way to the bottom, it will stop cutting. You notice in the close-up camera that the angle of the cut is changing the entire time. So at the top it was cutting at maybe a 30-degree angle, and at the bottom it's going to be cutting horizontally. If everything is set correctly and nothing is in the way, when I come around the back side, this screw will hit this right in, and it will shut this off automatically. There it goes. So the part came out. When you have a part that takes a considerable time to cut, the part may be hot, so I'm going to approach it carefully. This part is not that bad, but again, the part is going to have a sharp burr on the bottom edge, and the edges are going to be, generally speaking, sharp. Okay? So I'm going to bring this up to the camera. We'll take a look at the cut lines. So we have, if I can get this to focus, let me get my hand up behind it. We'll take a look at the cut lines. The cut lines are, again, indicative of the angle that the blade went down through. We should not see any major variations in that pattern. There is a pattern there, and essentially that is where we probably have something stuck in the teeth. We have maybe a bad tooth. On a brand new blade, that pattern would be very, very uniform, but we have a repetition in that. And again, we want to look at our parts as we're cutting to make sure that that pattern isn't changing considerably, because it could mean that we have a blade that's about to break. The other thing that we want to consider in a case like this is the sound of the cut. In the next segment, we'll look at different shapes, and we'll talk about the sounds. I probably am not going to break a blade, but if you hear a repetitive thump, 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 then you've got something going on. And at that point, you would want to stop, inspect the blade, and you may find that there's some teeth up. And we'll look at some damage and some still shots later on in the video. All right, we're going to take a look at cutting different shapes, some of the things you want to be concerned with. The first thing is pipe. I'm not going to let this cut per se because I don't want to destroy the blade. But what I will do is I'll show you a quick shot of what happens if the material isn't properly secured. Pipe is one of those weird sections, of course it's round, so it wants to roll. And there's no mechanical means of keeping the pipe from flipping. Like with an angle iron can be mechanically up against the backstop or something like that. We got to make sure that the pipe is tight. So when we tighten this vise down, I want to make sure, first of all, again, that you know that the bottom is tight, and also that the pipe itself is tight. And right now this is loose. And I'm going to bring this up to where it's just barely touching. And carefully I'm going to bring the blade down and we'll see what happens. I'm going to hold this in, kind of control it. And almost immediately it's starting to spin, right? If I wasn't holding on to that and I allowed that to happen, it would damage the blade. The worst case scenario is that it gets part way in the cut. Instead of being on the surface where it can roll smoothly, it's part way in the cut. And as it makes one partial roll around, it hits that deep spot, and then kablam, we've got a $55, $60 blade that's been destroyed, and maybe somebody got hurt. So again, we want to make sure that we get a good secure hold on the pipe. So we're going to go ahead and we're going to cut this piece of pipe the correct way. I've got this secure, and I want to have you watch on the close-up shot as the blade comes down through the material. We want to make sure that we are paying attention to how much blade is touching at any one time. So when the blade first hits the pipe at the top of the curve, at the point of tangency, I want to have the feed rate really low. And then as it starts to get into the cut a little further, where more than one or two teeth are cutting simultaneously, I can increase the feed. As it gets part way down through, of course it's going to be cutting on both sides at the same time, and then it'll come back around to a point. So pay attention to that. Power on, and then I'm going to open the feed up, bring it down close quickly, and then I'll shut that off, and I'll turn the feed on to a light feed. So right now there's a lot of blade in, and it's passing through the part. So the blade is passing through the part, connected on, only on two sides. As it gets near the bottom, the blade has now got more teeth in the cut, and then eventually it breaks through and stops. Okay? So with a pipe, no matter how you hold it, there will be a point at which there are really only one or two teeth in the cut at the tangent point, just beyond the tangent point. As it comes down through, it's supported at two places, although this pipe is thin, so there still might have only been a couple of teeth in the cut, but there's really not much else we can do short of putting on a blade that's much finer. But the sound of the cut was pretty decent. It wasn't too chattery. So again, that is pipe. we're going to take a look at is angle bar. The best way to hold angle bar is with it pitched up like a roof. Try that again. Pitched up like a roof. The reason for this is it just gives us more teeth in the cut more consistently. Essentially, at the very peak, when it first hits, it's really one tooth hitting at a time. We have to get down into the angle a little bit before multiple teeth are supported. So we want to start to cut slowly, let the teeth get in, and then once they're supporting themselves, if you will, 3, 4, 5 teeth in the cut, then we can increase the feed rate. And just like the pipe, as it goes down through, it's going to be supported on 2 sides. Unlike the pipe, it will continue to be supported at 2 points until it breaks through. So let's take a look at angle bar. A real slow feed in. And now that I got a couple of teeth in the cut, I can increase the feed rate a little more. Again, the angle bar is going to be contacted by the blade in 2 points, all the way down through the bottom. Listen to the cut. We're getting a little bit of chatter right now, but it's not too bad. So that chatter could be the result of the angle bar not being held flat against the bottom. Maybe some of the chips that are on the tabletop need to be vacuumed off. Okay, so I'm going to do that. We'll reset the angle bar. Alright, so I've reset the angle bar. I have the angle bar standing in a position that is not favorable to cutting. It will work, but again, it is not terribly favorable to cutting. The reason for that is that we're going to have really only 1, maybe 2 teeth in the cut on this vertical section all the way down. And then when we get to the bottom, we might have 10 or 15 teeth cutting simultaneously. So that is really not ideal. Listen to the sound of the cut as this goes down through. Now, as far as the cut being held securely, it's not really terribly bad because the part is going to be pushed into the backstop as we're cutting. So it's not likely to flip, but that doesn't mean I don't want to still have it held securely. So let's go ahead and cut. Again, I'm going to feed this really lightly until it gets started. Vibrating. Now that it's at the bottom, even though the feed rate is relatively high, it's taking forever to cut through that last 1/4 inch of thickness because there's too many teeth supported in the cut. If I went to a coarser blade, it would make cutting the bottom much easier, but the vibration on the vertical portion would of course be much worse. So again, while this works and it is safe, it is not an ideal way to cut this part. If we look at the close-up, I'll bring this up to the camera here, try to get this to autofocus. Right there. If we look at the close-up, you can see that wavy line in the vertical part. That's the result of chatter. That's the vibration that occurred as that went down through. And that's from one tooth hitting, being deflected to the side, the tooth coming in behind it, hitting, and then being pulled back to the middle, causing that vibration pattern. Okay. Again, we have long, straight sections on the bottom, horizontal grooves. I would say that there's one tooth that's probably a little bit bad. We're getting this constant pattern here as we cut of a scrape every, 1/16 of an inch or less. And then, of course, a wide chip burr on the bottom. So if you just want to work in the welding shop, you may not pay attention to those details. A machinist would definitely pay attention to them. And the difference between your blade lasting for a long period of time or your blade being destroyed in a short period of time is those details. So I would encourage you to look at it. Now we're going to look at one more way to cut angle bar. And I'm not going to do it because I know this will instantly break the blade. And I don't want to see you ever do this either. And this is with the angle bar held like so. I've got the angle bar in there tight, okay? It is actually fairly tight into the piece. What's going to happen if I come down and I start to cut here, this is unsupported, okay? The physical distance between this outside edge of the angle bar here where my finger is on the close-up camera and this back is fixed. And essentially the bottom point here at the bottom is a tangent point to the vise. Furthermore, the angle bar, if you can see on the close-up camera, is radius. So this will actually be allowed to pivot upwards with nothing preventing it. So essentially, I can take the angle bar and let me lift the blade up and get it out of the way. And even though it's in there tight, I can just pop it free. Never, ever, ever cut angle bar in this position. You're guaranteed to break the blade and probably get somebody hurt. Again, the correct way is always to cut the angle in this roof-like fashion. That is the safest, best way to cut angle bar. Moving on. Shapes like square tubing, doesn't really matter how you hold them. Both sides are tall, they're parallel, they're not likely to be positioned such that they can flip out, and as a general rule, it's almost impossible to cut these things incorrectly. Bear in mind, again, that on a square tube, we do have a situation where when this blade comes down and touches, initially, it will touch at just the close corner, like everything does. Depending upon the size and the thickness of the tube, there may be a period of time where the blade is 100% in the cut across the top. It's possible that it will break through on the inside corner, down here where my finger is, prior to cutting all the way through, and in fact we will not have mass numbers of teeth in the cut. But because the square tube is inevitably going to be flat across the bottom, we will have large numbers of teeth in the cut when the square tube gets to the bottom. Again, there's not a whole lot that we can do about that. If we go to a coarser blade to make cutting the top and bottom easier, it will create chatter as it goes down the sides here, okay? So that's it for square tube. I'm not going to cut it, but you can get it. Channel iron, or C-shape, C-section, is another piece that's a little bit difficult to cut. Essentially, the position that this is in right now, with the C facing down, is in fact the best way to cut this material. We will have a large wide face at the top to cut through, but even on this channel, which is only 3 inch, the blade will actually break through the inside here where my finger is before it cuts all the way out here, because the web of this channel is actually quite thin. So we will not have all of the teeth in the cut across the entire face of it in this position. As it passes through that going below, we will in fact have the blade supported in 2 places, just like pipe in the middle or angle most of the way. And therefore, this is the best way to cut this. If I stand the channel up vertically, I end up in a situation where I have a reasonable number of teeth in the cut while it's going through the upper and lower flange, but the web, which is very thin, with this particular blade, I will inevitably only have a single tooth cutting at a time, which means I'll have lots of chatter. If I flip it upside down, I will have the teeth supported in 2 positions for most of the way down, but by the time it gets to the bottom, because the blade is nearly parallel to the deck, I will have a situation like this. Maybe you can see it in the close-up camera, where all of the teeth will be cutting simultaneously. And while there's no unsafe way in any of these positions to hold it, I would say that with the channel vertical would be the absolute least desirable in terms of blade performance. Upside down would be second least desirable, and this is the best way. So we'll make a quick cut, and you can watch the blade in the close-up camera as it passes down through. And again, note where the blade is supported, and keep in mind how many teeth are cutting simultaneously. So right now the blade is actually broken through on the right-hand side, and by the time it breaks all the way through, it's virtually in the angle, in the legs, and relatively quickly it goes through. That screaming noise that you're getting, that high-pitched whine, is the chatter pattern as this goes down through the part. And again, I'll pull this up to the camera, and you can see that chatter pattern occur if I can get the camera to actually focus. God knows where this thing's trying to focus, but not on my hand for sure. We can get that pattern here anyway on that front edge. So again, that is not ideal, but it is relatively difficult to eliminate it completely. All right, the last thing I want to talk about in terms of general cutting in the shop, without getting into job-specific tasks or unusual things that may come up as a part of a project, is cutting stacks of material. Whenever possible, material needs to be held as securely as it can be. We typically in this shop don't cut bundles of material, but it is not uncommon for that to happen at the machine shop at BIW. It's not uncommon for angle bar to come in for the pipe shop to make pipe hanger legs, and they make by the tens of thousands. And that material will be bundled into a ball. It'll be pulled right up tight and secured with steel banding, and then it will be cut through. This blade is actually designed for that, this Starrett Versatix blade. Again, awesome blade, but again, we don't do that here in the shop. One thing that is common, or used to be really common, before the shear came along, was cutting welding school practice plates, and we would typically cut stacks of them. All right, what I have here is I have a stack of overhead practice plates. Essentially, they are a large bundle, and we put them in a large bundle on the saw so that we can, let the saw go pass down through, and we get 10 or 15 parts instead of one part at a time. For this particular stack, I am not really exceeding the number of teeth in the cut that I would have with this particular blade, although I could go with a coarser blade if I felt I needed to. So it doesn't make a lot of difference which way I orientate this. This stack is about the same height as it is wide, give plus or minus maybe a plate or two. The issue here is not how many teeth are in the cut, but it's whether or not the part will stay in place. What happens when we have a large stack like this is it's like the game Jenga. And essentially, while this material is in theory all exactly the same width, the reality is there is slight variation. So when the vise comes in and pulls, first of all, the vise is being pushed on from above where this part is, so it tends to want to tip like this. And what we end up with is a situation where we have parts that are not necessarily secure. In this case, the top part's not held at all. The rest of them are all fairly tight. In other cases, we may have a situation where halfway through the stack, a piece starts to vibrate and come loose, and that can cause damage to the blade. So the better option, although it's difficult when these are long, and this is why people like to stack them this way, the better option is to stand the parts in this manner. The reason for that is the parts are sandwiched on one another in such a manner that they really can't slide. I'm not relying on the edge thickness to be precise to make these fit. Okay? In the game Jenga, the old game with all the blocks that you pull, those blocks are all the same size. Okay? They're not intentionally machined, some bigger and some smaller, some thicker and some thinner. They're the same size. But the reality is that tiny, tiny, tiny variations add up and allow one block to slip free when it's supported on two other positions. By turning this on their side, every block is forced to push on every other block, and there's no way for this to slip. So having this angle bar pack stood up vertically is in fact the way to go. Obviously, we would want to still keep in mind how many teeth are in the cut. I wouldn't want to have 30 of these plates stacked out here because it would exceed that limit. But by doing this, the parts A will not come out of the cut until they've all been cut. And B, they won't slip. Okay? with the other scenario, if I roll this back, one of the problems is that as soon as the blade makes it through the top piece is trying to fall off. And then the piece below is trying to fall off. So not only do we have parts coming out of the stack, which is potentially dangerous, throughout the cut, but we have again a situation where if one plate is slightly narrower, in this case I can get a hold of this middle part right here. Top is a little bit loose. I get the whole bottom tight. And I can pull the other half of the stack around, even though I can't move the bottom. So again, that is not the correct way to stack them. Stand them on their edge, like I said, the textbooks in the library, crush them together, and then make your cut. All right, so we've gone ahead and we've cut the common shapes that are here in the part. We'll talk maintenance in another video, replacing blades and things like that, kind of more advanced tricks and tips and techniques. The only other thing really that we have to mention in terms of basic setup is cutting at an angle. In terms of cutting at an angle, the important thing to remember is that we have to lift the head before we rotate it. When the blade comes down, it cuts into this table, so the blade is lower than the upper surface of the table. And if we try to rotate it, it will damage the blade. So we simply have to lift the head up, lock this position, and then if I come around to the back side of the blade, that's shown earlier, a little lever right here, and I can actually push that in the off position with my foot, okay? But of course I still have to reach under to pull it on. I simply loosen it, adjust the angle on the scale that's on the back side, and then pull this back and lock that down. Cutting operation is exactly the same at an angle as it is for anything else. So the angle cutting is something that I will not demonstrate in this particular video because I will cover beveling welding plates, which is a little bit different, in another video a little bit later on. But that's the basic operation of this saw, folks. So drop the head, make sure everything's off, kill the auto stop button. I think that's the safest way to put it to bed, and be safe.